Partial differentiation application part 2. Conditional optimization by using the Lagrange method. The Lagrange method is the method to calculate the extreme value of a function that faces constraints in the form of another function. And to form this, to make the function, the main function with the constraint, be a one function, we will form a new function and we call that as the Lagrange function. The Lagrange function will be started from this main function first. This is the same like what we have discussed last week. We want to optimize this kind of function. Okay, and then the difference between what we have done last week with today is that we have another additional function which make this function have a constraint. So we call that as a condition, and that condition will contain also a function with an independent variable such as this function, the same one, two variables which are x and y. And by this, these two functions, we will combine it as one function, and this is what Lagrange has found. And the condition will be, the function will be like this. So we will rewrite the function as big F, and it will contain no longer two variables, but we have another one here as a lambda, and this big F function will be the small f, the z, plus lambda u. So I will rewrite again here, x, y, lambda actually is the z plus lambda u. Okay, so Lagrange has thought about this additional function to fill in here, and we now change the z with the f, x, y, and here is lambda times g, x, y. Okay, so this is what Lagrange has found. Next, the steps in determining the optimization function with constraints. So like previous optimization without constraint, first of all, we have to determine the first partial derivative, and also it should be equal to 0. So this one is to find the points, the stationary points. Okay, so here is dou f dou x. Dou x, it should be equal with 0, and then dou f dou y equal with 0. We have another one since that we have the third independent variable, so lambda, dou f dou lambda should be 0. Then after we have three variables with three equations. Okay, so we have to make some elimination way or substitute. All right, then after we find the points, we have to determine whether the utility function or the maximum objective function must meet two conditions. Namely, first of all, we have to find the second direct partial derivative and also the cross partial derivative. It's like dou f quadrat, dou quadrat f dou x quadrat, and dou quadrat f dou y quadrat, and also dou f dou x dou y, right? And also, so this is fxs, this one. Then fyy, dou f second derivative y, and this one is the partial one, second derivative of partial, and also we have gx gy. So we have over there that this should be like this, this is the constraint subject to, or the constraints So again, this is the constanta and this is the function. So this one, we have to determine the function of g, and we need to find out the derivative of g against x and then do g against y. Then we form a Hessian determinant. Okay, this is the determinant that is formed through the Lagrange, the thing that we need to find out for which one has the maximum or the minimum value through this determinant. Since I haven't taught you guys about the matrix yet, I need you to memorize this. So this, from this determinant, we get the form in algebra. So this is 2 times the first derivative of g through x. This is the first derivative g of against y, and this is the cross second partial derivative, and then minus gy dou g dou y quadrat times the second derivative of x, and then this is dou g dou x quadrat, and oh, there's no zero here, times second derivative of a against y. And if the value of these things bigger than 0 or positive, so we call that the function has a maximum relative, and then vice versa, if it is negative, the function has a minimum relative. All right. Okay, now we are going to do an example here. Determine the extreme value of z equal xy, provided x plus 2y of 10. So given here, so our main function, given main function or primary function that we want to see what kind of value that it has is z, which is xy, and this main function subject to or constrained by g xy equal with c. Yeah, and this is x plus 2y c 10. So c here is a constant. Okay, so we have here g as here and c. Okay, and we make the Lagrange form, so as f x y lambda. Okay, oh, first of all, I forgot about this. All right, so basically this is the main function, right? So we want to make the function, the new function, as subject to this constraint without changing the xy itself. So what is that actually? So if I wrote again our rule here, so like this, well, basically if we don't want to change this should be 0, right? So therefore we have to make the g over here next to lambda is just like we make it as a 0, and if we put here 0, it means that the left side here goes to the right, became like this. Okay, so therefore the main function here xy and then lambda times 10 minus x plus 2y. Okay, so this is our main function right now. I'll open the brackets, lambda x, be careful with this minus positive sign here, 2 lambda y, right? So this is our main function. Okay, and then we apply the rules to find the extreme value. So first of all, by finding the points, stationary points, by defining dou f dou x, which is, see, okay, look over here, see, this is the f. If we derive that with against x, it will be y, and here is 0, and here is minus lambda. And the rule is to apply dou f dou x should be equal with 0. So y minus lambda is 0, so y is lambda, or lambda is y. Okay, next is dou f dou x. This is my first equation. Sorry, dou f dou y as the second first derivative over here. Look again here. Okay, so derive it with against y. It will give you an x. Here y, 0. Here, 0 also. And this one against y is minus 2 lambda. And we apply that dou f dou y should be 0. X minus 2 lambda equal with 0. So x is 2 lambda. So this is my second equation. If we substitute 1 to 2, it will be, so x minus 2 lambda here is okay, like this is the 2, and here y is equal with lambda. It means that this should be like this. So this is my third, right? Okay, next is the first derivative of f against lambda. Right, I will write down again xy minus 10 plus 10 lambda minus lambda x minus lambda 2y, okay, or 2 lambda y. Let me see here, 2 lambda. Okay, so that's our main equation, and then we derive this with lambda. So here 0, here is 10 plus 10, here is minus x minus 2y, and we apply this to f. The y should be equal with 0, so it is 10 minus x minus 2y, x 10 x plus 2y, or x plus 2y equal with 0, 10. So this is my fourth equation, and apply that x is, apply 3 to equation 4. You know that our third equation is x plus 2y, so x plus 2y is 10. This is x equal with 2y. This is the third, this is the fourth, right? So change this with the next. X plus x is 10, so 2x is 10, x is 5. Okay, and substitute x equal with 5 to the third equation. So x is 2y, 5 is 2y, so y is 5, 2, or 2.5, and substitute okay, now we go to prove whether that point is maximum or minimum by applying the rule number 2. Determining maximum or minimum value Okay, now we will define the derivative, second derivative of x. Okay, I recall, where should I write? I'll write here down. So recall from the second last slide that I have here dou f dou x equal with y minus lambda, and then dou f dou y is 2x minus lambda. Okay, so the second derivative of x will be from here. So look over here, there is no x at all, so the second derivative of that function will be 0. And next, dou quadrat f dou y quadrat, look over here. Yeah, so there is no y, so if you derive it again against y, it will be 0. And what about second derivative of dou x dou y? Yeah, look again, number 1 over here. So this already derived against x, and then next is y. So look over here, it has y here, and the derivation of y is 1. And also here, it is already derived against y, and then we derive it against into, oh, I was wrong here, it should be x minus 2 lambda. So dou f dou y, then derive it again into against x, it will be 1. So the same. Okay, now next is we have to define dou g dou x and dou g dou y. I will recall again here that our function of g is equal with x plus 2y 10. Yeah, so the function of g here is x plus 2y. So here, constanta with constanta, and the rest is the one with x and y. Okay, so if you derive that g against x is 1, and this against y is 2. Now we go to the Hessian determinant. Hessian is 2 times the first derivation of g with x and y, and then times the second derivative xy, then minus gy quadrat times f xx, second derivative of x, minus gx quadrat fyy. So it gives you 2 times 1, should be like this, 1 times 2 times 1 minus 2 quadrat times 0 minus 1 quadrat times 0. Yeah, you should fill in here. Fxx is this one, fyy is this one. Okay, so that will give you 4, and this is bigger than 0, so maximum relative. Yeah, so the conclusion is that at x, the function has maximum relative at x5 and y 2.5 with lambda also 2.5. Okay, I think that's enough for this part. I will continue with another exercises. Thank you.